Anticipation consumed the atmosphere as they saw the hotly anticipated enactment of the most progressive high-energy molecule collider. After quietly hanging tight for many years, they at long last viewed this surprising innovation, ready to change our cognition of the universe. The enormous Hadron Collider, built by the European Association for Atomic Research, became functional in September 2008 after a meticulously extended development stage. However, it took the machine's designers quite a long while to perfect it. From that point forward, the enormous Hadron Collider has had an essential impact in disentangling various conundrums of the universe during its different trial runs. All things considered, ongoing developments have raised concern among researchers at CERN. After ramping up the enormous Hadron Collider to a new pinnacle energy level, they detected something surprising and startling. Subsequent investigations have prompted various hypotheses attempting to make sense of this peculiarity. Yet, at this point, they remain unconfirmed and speculative. The universe has a multitude of unexplained secrets, and throughout the years, researchers have dedicated their time to research, trying to comprehend and make sense of some of them. These secrets include the enormous black hole seen in space, which is said to have such a strong gravitational pull that even light can't escape, and also what lies beneath the Bermuda Triangle, called Satan's Triangle. It is well known for the mysterious disappearance of more than 50 boats and 20 airplanes, yet they remain unexplained due to limitations in technology. In the mid-20th century, physicists searched for better ways to explore the fundamental building blocks of matter. In 1932, physicist John Douglas Cockcroft and engineer Ernest Walton developed the first functional atom smasher. These particle accelerators are fundamental tools for investigating the key constituents of matter. By accelerating particles to high energies and colliding them, researchers can study the subsequent interactions and test the fundamental forces in particles that make up the universe. Given how valuable particle accelerators can be in making sense of the secrets of the universe, CERN has built the world's largest atom smasher. Yet, researchers have made the alarming discovery that this atom smasher could potentially cause the Mandela effect due to its ability to alter the fabric of space and time. What are the implications of this revelation? Many people wonder why they remember things differently from how they actually happened. This is a phenomenon known as the Mandela effect. The term was coined in 2009 by Fiona Broome. She discovered that she and many others mistakenly thought Nelson Mandela had died in the 1980s, though he passed away in 2013. Several factors can cause this effect, such as false memories and the strong influence of social media and the web. However, some researchers have raised concerns that past power-ups of the LHC may have also caused the Mandela effect. Before dismissing this theory as paranoia, note that some prominent researchers and other notable figures have expressed concerns. Stephen Hawking was one of the first to voice his worries about the impact of the Large Hadron Collider. He warned in an interview that the collider could create black holes that might threaten the universe. Another researcher, Dr. Carlo Rovelli, expressed his concerns about the LHC in a blog post, suggesting that it might create speculative particles that could transform surrounding matter into something new. Even figures outside of science have discussed the potential risks associated with the Large Hadron Collider. Astrophysicist Carl Sagan and sci-fi writer Arthur C. Clarke also voiced concerns about the collider, proposing the creation of strangelets or even a black hole that could swallow the Earth. In a press conference, President Obama also expressed his worries about the collider causing a catastrophic event that could affect reality. The fact that several groups of significant individuals, from scientists to scholars and notable people, have expressed anxiety about the LHC highlights the seriousness of these concerns. While we cannot predict the outcomes, it is important to carefully consider the potential risks and make informed decisions about operating the collider. So, is CERN's LHC capable of causing the Mandela effect and other changes in our universe? The Large Hadron Collider is currently the largest and most powerful atom smasher in the world. It was built between 1998 and 2008 in collaboration with over 10,000 scientists from more than 100 countries. It became functional on September 10, 2008, and is the most recent component of CERN's accelerator complex. The goal of this atom smasher is for physicists to test the predictions of various particle theories, including estimating the properties of the Higgs boson, searching for the large array of new particles predicted by supersymmetric theories, and investigating other unresolved questions in particle physics. The collider appears as a 27 kilometers ring made of strong magnets and structures that make particles go faster and gain energy. Inside the accelerator, there are two beams of energy particles moving at incredible speeds, nearly as fast as light, before being directed to collide. These beams travel in opposite directions through isolated tubes called beam pipes, which are kept at very low pressure. The beam pipes then follow a circular path around the accelerator due to a strong magnetic field produced by superconducting electromagnets. The magnets are made from coils of special electrical cables that work in a superconducting state, allowing electricity to flow without resistance or energy loss. To maintain this superconducting state, the magnets must be cooled to a temperature of -271.5 degrees Celsius, colder than outer space. To achieve this, a system of liquid helium is used to cool the magnets, along with other crucial air supply systems throughout the accelerator. Running at an energy of 6.5 trillion electron volts per proton, the LHC accelerates protons from 450 GeV, giga-electron volts, to 6.5 trillion. During this process, the magnetic field of the superconducting dipole magnets increases from 0.54 to 7.7 teslas. The collision energy of the protons reaches an impressive 13 TeV, tera-electron volts. At this energy level, the protons achieve a Lorentz factor of about 6,930, moving at a speed of approximately clees and explore their interaction. 0.99999 times the speed of light. The time it takes for a proton to complete a full circle around the main ring is under 90 microseconds, resulting in an astounding 11,245 cycles per second. The journey of protons in the LHC begins in a linear accelerator, LINAC-4, that produces negative hydrogen ions at 160 MeV, mega-electron volts. These ions then travel through the proton synchrotron booster, where electrons are stripped away, leaving just the nucleus with a single proton. The protons are then accelerated quickly to 2 GeV and enter the proton synchrotron, reaching an energy of 26 GeV. Finally, the superproton synchrotron boosts its energy to 450 GeV before injecting them into the main ring. In this ring, protons are accumulated, accelerated rapidly to their peak energy over 20 minutes, and circulated for 5 to 24 hours, allowing collisions to occur at the 4 intersection points. While the primary focus of the LHC physics program is proton collisions, it also has dedicated periods, usually 1 month per year, for heavy ion collisions. Lead ions are the preferred choice for this program and are accelerated to an energy of 2.3 TeV per nucleon or 5.02 TeV per particle. The LHC operates with a vast amount of energy and produces massive data collections, illustrating the immense scale and significance of this scientific endeavor. The CERN site draws around 200 megawatts of electrical power from the French grid during LHC operations, which is roughly 1/3 of the energy consumption of the city of Geneva. Notably, the LHC accelerator and detectors contribute around 120 megawatts to this demand. This energy surpasses that achieved by the relativistic heavy ion collider. The heavy ion program aims to investigate quark-gluon plasma, a state of matter believed to have existed shortly after the Big Bang, providing crucial insights into the fundamental nature of matter and the universe. With the help of this particle accelerator, one of the significant theories in particle physics regarding the Higgs boson has been confirmed. The Higgs boson, often referred to as the God particle, made its appearance at CERN in 2012, marking a significant breakthrough in the field of particle physics. If you're wondering how the Higgs boson got its nickname, it's from a book titled The God Particle by Leon Lederman, published in 1993. However, this nickname has faced criticism from many physicists due to its potential to mislead the public. The Higgs boson is a subatomic particle in the standard model of particle physics, produced by the excitation of the Higgs field. In the standard model, the Higgs boson is a massive scalar particle with zero spin, electric charge, and color charge. It is associated with mass, as the particle decays into various other particles very quickly upon its creation. The Higgs field, shaped like a Mexican hat, is an invisible force field with different parts that are both electrically charged and uncharged. This unique field influences how particles interact, giving them mass through a process known as the Higgs mechanism. The Higgs boson and its field are named after Peter Higgs, who, along with 5 other researchers, proposed the existence of this particle in 1964. This proposal was the only explanation for why some particles gain mass after looking for 40 years. Researchers eventually found a particle with similar properties to the proposed Higgs boson at the LHC. Finding the Higgs boson as predicted was crucial because it helps us understand why some particles have mass, a fundamental property that affects how things behave and explains how elements in the universe interact with each other and form the basic building blocks of matter. To create Higgs boson particles, researchers use 2 beams of protons and collide them in special detectors. These detectors have sensors that measure and track the collision's outcome, helping researchers identify the Higgs boson part 1.